So you want to make a computer chip. Perfect. Let's start by taking away your computer. 1 second, you're sitting at your desk. The next, everything disappears. You're dropped into a blocky desert with an empty inventory and no electronic store in sight. There is only one useful object nearby, a pale rock sitting in the sand. That rock is quartz, and somehow, by the end of this video, we're turning that ordinary rock into the brain of a computer. We need to solve 3 problems: pure silicon, 1 perfect crystal, and billions of switches drawn with light. Easy enough. Pick up the rock and put it in your inventory. It's the only free item you're getting today. You could collect beach sand. That would give you a lovely bucket of sand, but not a computer chip. What we actually need is cleaner quartz, a rock in which silicon and oxygen are locked together. Silicon is a semiconductor, so we can make it block electricity in one place and pass it in another. That ability will create microscopic switches. For now, the silicon remains trapped, so the quartz goes into our inventory. Next, we need to free the silicon. For that, collect carbon and find a very large electric furnace. Not your kitchen oven. We need an industrial furnace built for extreme heat. Quartz and carbon go in. The temperature climbs, and the carbon helps pull the oxygen away from the quartz. This isn't delicate chip making yet. It's heavy industry, molten material, and several reasons not to touch anything. When the furnace opens, the pale quartz is gone. In its place is a dark, metallic chunk of raw silicon. Good. Put the raw silicon in the inventory. It looks impressive, but it is nowhere near ready for a chip. Unwanted atoms can change how electricity moves through an area too small to see. So now we know exactly what the next item has to be: silicon that is almost impossibly pure. The raw silicon enters a purification chain. Now crafting means removing everything that isn't invited. Step by step, unwanted material is separated out, and the silicon is rebuilt as clean pieces of polysilicon. Its purity percentage has a ridiculous number of 9s. We'll show it instead of sounding like a broken calculator. The refinery checks the material again. Red lights turn green, and the ugly metallic chunk becomes clean, silver-gray silicon pieces. That's the ultra-pure silicon we needed. Put it in the inventory, and please keep it away from the desert. Purity solved. But these pieces contain crystals pointing in different directions. A chip needs one consistent foundation, so now we've got to turn the entire pile into one crystal. Drop the pure silicon into a quartz crucible. Heat it to roughly 1400 degrees Celsius, and the solid pieces melt into a shining pool. Lower a tiny seed crystal to the surface. This seed determines how the giant crystal will be arranged. Pull the seed upward very slowly while everything rotates. The molten silicon begins copying the seed's atomic pattern. One continuous crystal rises from the liquid like a smooth metallic tree trunk. There it is, a silicon ingot, wider than a dinner plate and taller than a person. Add it carefully. It's extremely heavy, and Scrib has remembered the inventory's weight limit. Perfect crystal solved. We've made an incredibly orderly object. Naturally, we're about to cut it apart. The next item we need is a flat surface for our circuits. A precision saw cuts the ingot into thin, circular slices. Fresh from the saw, each slice is scratched and rough. Microscopic circuitry needs something much flatter, so the slices are ground, cleaned, flattened, and polished with extraordinary precision. The result looks like a dark mirror. Now we have a silicon wafer, the building platform for our chip. One wafer carries many copies of a chip, arranged like plots on a circular map. From this point forward, dust is the enemy. A speck can destroy a structure much smaller than the speck itself. Put on the clean suit: gloves, mask, hood, even shoe covers. Fashion has left the building. The wafer is ready, Scrib is dust-free, and we're entering the fabrication plant, or fab. Engineers begin with a blueprint for every component and connection. Parts of that blueprint are transferred onto special masks. Each mask carries a pattern for one part of the chip. First, a machine deposits an extremely thin layer of material across the wafer. Then the wafer receives photoresist, a coating that changes when it is exposed to light. To print the pattern, the wafer enters an extraordinarily precise lithography system. Light passes through the pattern on a mask. At the moment, the image is still much too large for a chip. A complex optical system shrinks and focuses that pattern onto a tiny section of the wafer. Where the light hits, the coating changes. The invisible blueprint has now been transferred onto the surface. The wafer is developed, and selected areas of the coating are washed away, revealing the material underneath. Another machine etches into those exposed areas. Think of it as a stencil, except the drawing is measured in nanometers. Other machines add materials or place selected atoms into precise regions. That changes where electricity can flow and where it cannot. Together, those regions form transistors, microscopic electrical switches with no moving parts. Then we repeat the process: coat, expose, develop, etch, inspect, and again, and again. Scrib has stopped asking how many times are left. Each loop adds more circuitry. Some modern chips contain close to 100 carefully aligned layers. Layers of metal connections are added between the transistors, allowing signals and power to travel across the chip. The blank disk becomes an electrical city. Transistors are the buildings, metal connections are the roads. After months between machines, the final layer is finished. Billions of switches are in place. Now we need to find out which chips actually work. The finished wafer is covered with repeated rectangles called dies. Each die is one tiny piece of silicon that could become a computer chip. Could become. Some dies still contain defects. Tiny probes touch test points across the wafer. A test map appears. Green rectangles pass. Red rectangles fail. There is no participation trophy for a broken transistor. The working dies can also perform at different levels, so they are measured and sorted into groups. Once testing is finished, a precision saw cuts along the narrow streets between the rectangles. One wafer becomes hundreds of separate dies. We only need one good piece for our final craft. Scrib reaches for the nearest one. No, red square, put that back. Try the one next to it. Green, much better. The working die goes into the inventory. The die has complete circuitry, but it's fragile and cannot connect to a computer yet. We need one final item, the package. First, place the working die onto a supporting substrate. Add tiny electrical connections so power and signals can move between the silicon and the outside world. Protect the delicate die with a package and, when needed, place a heat spreader on top. Final recipe: one working die, one substrate, electrical connections, one protective package. Combine, and there it is, a finished computer chip. Try not to drop it back into the sand. Our ordinary desert rock is now an electrical city, built in layers too small to see. The strangest part is that factories repeat this process daily and produce chips by the wafer. Take the chip back to the computer and place it carefully onto the motherboard. The screen lights up. A journey that began with desert quartz ends with a working computer. Craft complete. Now that we have a computer chip, what should we build with it?